Hi everyone. In today's lesson, we're going to talk about a concept called implicit differentiation. So first we need to talk about the difference between explicit differentiation and implicit. So explicit differentiation, or an explicit function, is a function in which one variable is defined only in terms of the other. So for example, y is defined all in terms of x. Same here, y is defined in terms of x, y equals everything that's equal to x, right? So y on one side, x is all on the other. Implicit differentiation, or an implicit function, is found in which one variable is not defined only in terms of another, meaning we have x squared plus y squared, then 9. So the y is not alone like it is on these three here, right? So it's x squared plus y squared minus 4x, right? Y's are inside here and here. Y's would be here, here, and here, all different places. So we use the concept of explicit differentiation when the equation is already solved for y equals, like here. And we would use implicit differentiation, like here, when it's difficult to solve for y, to isolate it by itself. So basically, when there's a whole bunch of other things there, we'd probably want to use implicit. And then applications we can use once we find dy over dx, which is my derivative, right? dy over dx is derivative. So once we find the derivative, we can use it to find the equation of the tangent and normal lines at given points. So let's start off with a nice small example. So it says, find the derivative using explicit and implicit differentiation. So if I were to use explicit, I need to get the equation in y equals. So I'm just going to rewrite this. Y minus x squared minus 2x equals negative 3. So if I wanted to get y by itself, I would add x squared and add 2x. And I can put this in standard form. So x squared comes first, then 2x, and then minus 3. So if I want to find dy over dx, or the derivative, I'm going to take the derivative of all of these pieces with respect to x. So power rule, take the 2, drop it in front, keep the base, and subtract the power by 1. And the derivative of 2x is just 2. Derivative of a constant is 0. So to simplify, my dy over dx is just going to be 2x plus 2. Now we can do the same thing using implicit differentiation. So implicit differentiation implies that everything stays where it is. So what we can do is take the derivative of each of the pieces separately. So the derivative of y is dy over dx. The derivative of x squared, bring the 2 in front. So minus 2x, drop the power down by 1. The derivative of negative 2x is just negative 2. And the derivative of our constant 3 is 0. So now all we have to do is get dy over dx by itself on one side of the equal sign. So I can add 2x on both sides and add 2. So dy over dx, my derivative, is equal to 2x plus 2. So same thing either way. All right, let's do an example where solving for y might not be so easy. So here, to get y by itself, you would have to subtract the x squared and then take the square root. You'd have the plus or minus. So it's probably a lot easier if we use this concept called implicit differentiation. So what we're going to do is, just like we did in the first example, we're going to take the derivative of each piece. So the derivative of 2x, x squared is 2x. And the derivative of y squared is 2y. But since we took the derivative with respect to y, we have to write times dy over dx. And then we keep going. What's the derivative of 9, which is a constant? You get 0. So since we have to find dy over dx, we should probably isolate this. So we're going to subtract 2x on both sides. And we get 2y times dy over dx equals negative 2x. And we divide both sides by 2y to get dy over dx by itself. So dy over dx is negative 2x over 2y. Now, if you wanted to simplify it, the 2's can cancel. So your dy over dx is negative x over y. So this is your answer for part A. So part B is asking now to find dy over dx, find the derivative at this point. So for part B, all we have to do is plug this point, negative 3, 5, in for x and y in our derivative. So dy over dx, the derivative is negative x over y. So since my x is negative 3, it's negative 3 over my y, which is 5. So positive 3/5 is my dy over dx at this point. So if we remember, dy over dx is my derivative. So this is my derivative or my slope of the tangent line at x equals negative 3, right? That's the x value of the point. So slope of the tangent line at x equals 3. All right, let's try a more difficult example. So we need to find, same thing, find dy over dx using implicit differentiation, and then find dy over dx, or the derivative, at this point. So implicit differentiation says we can take the derivative of each of the pieces. So the derivative of 2x, x squared, is 2x. The derivative of y squared is 2y. But we have to remember, we took the derivative with respect to y. So we have to write dy over dx. The derivative of negative 4x is negative 4. The derivative of 5y is just 5, but I took a derivative with respect to y, so I have to write dy over dx. And then minus 8, but sorry, the derivative of 8 is actually 0, and the derivative of 0 is 0. So again, derivative of x squared is 2x, derivative of y squared is 2y, but since I took the derivative of y, I have to multiply it by dy over dx. Derivative of negative 4x is negative 4, and the derivative of 5y is just 5, but since I took the derivative with respect to y, I need to write dy over dx. The derivative of a constant is 0. The derivative of another constant is also 0. So the goal is going to be to get the dy over dx's to one side and everything else on the other. So I want to subtract this 2x on both sides. And simultaneously, I would like to add this 4. So add 4. So my left side, I have 2y times dy over dx plus 5 times dy over dx equals negative 2x plus 4. So now some of you might be thinking, well, there's two dy over dx's, so how am I supposed to get them alone? Well, what you can think of is you can actually take out a dy over dx as a GCF. So if you divide this term by dy over dx, you'll be left with 2y. And if you divide this term by dy over dx, you'll be left with 5. So taking out that GCF will actually help you simplify. So then, since this dy over dx is attached to this by multiplication, we can divide 2y plus 5 on both sides. So my final answer for my derivative, dy over dx, is negative 2x plus 4 all over 2y plus 5. So this is my answer for part A. Now, part B is asking us to find the derivative at this point for negative 1. So part B is the same as we did in part A. In question number 1. So part B, to find dy over dx at for negative 1, you're going to plug x to be 4, y to be negative 1 into my derivative function. So my dy over dx is going to be -2 times x, which is 4, plus 4, over 2 times my y value, which is -1, plus 5. So this is -8 plus 4 is -4. And this is -2 plus 5, which is 3. So my dy over dx at the point 4, -1 is -4/3. And what this is your slope of the tangent line at x equals 4, right? That specific x value. All right, that's it for implicit differentiation. If you have any questions, now is a good time to jot them down, and we'll go over it in class tomorrow. Have a good night.